This just says that if you multiply two things together with the same base, then you add the exponents. That's it. That's why it's called the additive law of exponents, because you're adding exponents. It's a very literal name. So this works the way we expect it to. For example, you have 3 to the 4th times 3 to the 7th. You're just going to add the powers and get 3 to the 4 plus 7, which is 3 to the 11. We don't want to write, I don't want to write out 4 3s multiplied by 7 3s, right? That's a lot of space and time. We're trying to make this as compact as possible just to make our life easier. Or we could say, right, you don't have to have numbers as your base. You could have variables like x to the 6th times x to the 8th. And that would be x to the what?
14.
Yeah. We have to use our adding skills. Sometimes the adding is easier than others. It also works whether or not your base is positive or negative. I should point out, technically sometimes a can't be 0. Usually we don't really care about the base being 0 because 0 to a power is not very interesting. But I just want to point that out, that sometimes it's a problem. We can get more into it later. But the additive law of exponents really does work for any other base. It definitely works for negative bases. For example, if I have -2 to the 3rd times -2 to the 5th, that's going to equal -2 to the 3 times plus 5 is 8. It is important if your negative number is in parentheses that it stays in parentheses. Right? -2 to the 8th is actually going to end up being a positive number because it's a negative number times a negative number an even number of times. That's going to be positive 256. Whereas if we had, like, say, -2 to the 2nd times -2 to the 3rd, that would end up being -2 to the 2 plus 3, which is -2 to the 5th. And that would end up being negative because it's a negative number multiplied by itself an odd number of times. We can write this one out. It's not too many 2's. -2 times -2 times -2 times -2 times -2. 4, -8, positive 16, -32. So depending on, so if your base is negative, if you end up having a negative base to an even power, it's going to end up being positive in the end. If you have a negative base to an odd power, it's going to be negative in the end. And it's just because of the number of negatives you multiply together, right? Here it's an even number of negatives, so it ends up changing signs to the right number of times to end up being positive. Here it's an odd number, so you change signs enough times to be negative. And then I should also say it works if you have more than just 2 terms. For example, if I had 5 squared times 5 cubed times 5 to the 7th, I can just add all the powers here. So that's going to be 5 to the 2 plus 3 plus 7, which is 5 to the 12th. Again, a lot of these numbers are going to be way too big. Right? I don't want you, like if I asked you to do this on your homework, I don't want to know what 5 to the 12th is. It's a really giant number. I don't care. I just care that it looks like 5 to the 12th. And then I should point out, if we have different things mixed together, for example, if I had like x to the 4th times y cubed times x to the 8th times y squared, different bases can't go with each other. So like I can put the x's together and the y's together, but they can't like mix and match. So I could totally write this as x to the 4 plus 8 times y to the 3 plus 2. And that's going to be x to the 12th times y to the 5th. That's about as simple as I can make that expression. So as long as the bases are the same, we can add the powers together. As long as we are multiplying things together where the bases are the same, then we can add the powers together. What if now instead we're dividing? What if I have 2 to the 5th divided by 2 squared? Well, there's a couple ways to think about this. I'm going to go 2 different ways. One way is actually just to multiply it out. If the number, here the numbers are small enough that it's not too hard to do. 2 to the 5th is 32. 2 squared is 4. And 32 divided by 4 is 8. Which is 2 to the 3rd. Another equally good way to look at it is to say 2 to the 5th is 2 times 2 times 2 times 2 times 2. 2 squared is 2 times 2. And we're dividing here. 2 divided by 2 is just 1. 2 divided by 2 is just 1. So I'm left with a 2 times 2 times 2 on top over 1. But anything divided by 1 is just itself. So you get 2 times 2 times 2. I was going to try and be on the other side of the room. Okay, chair. So when we are multiplying things together with the same base, we can add the powers. When we're subtracting things with the same, sorry, when we're dividing things with the same base, we can subtract the powers. And so generally we have the following rule, that a to the r divided by a to the s is equal to a to the r minus s. And here it's a little more obvious why 0 might be a problem. If you had 0 to a power in the denominator, you'd be dividing by 0, which would be undefined. So usually we don't think about our base as being 0. We don't give this another name. This is still the additive law of exponents. I will show you a little bit later how this is really just the same rule as the additive law of exponents, but we're not quite there. So yes, we'll come back to that. Also, I cut my thumb yesterday, so it's hard for me to turn the pages, but I will do my best. Also, it's left thumbs, really important for buttoning buttons, like, or for on men's shirts, really important for buttoning buttons. So it's, buttoning the shirt was a little bit challenging. It's all right though. I survived. Real tough time, yeah. I could have just worn a t-shirt, but I like this shirt. It's a fun shirt. It's one of my favorites. I'm sure you guys have seen it a few times already. Not that you're like cataloging my wardrobe or anything, but anyway, let's get back on topic. So here's some examples. 3 to the 8th divided by 3 to the 6th is just going to be 3 to the 8 minus 6, which is 3 squared. And depending on what we're asking for, we could leave it like this. Here it feels also very easy to write that it's equal to 9. We can have variables. X to the 23rd divided by x to the 11th. It's going to be x to the 23rd minus 11, which is x to the 12th. 2 to the 4th divided by 2 to the 7th is going to be 2 to the 4 minus 7, which is going to be 2 to the negative 3rd. Now, I know we haven't talked about negative powers yet, but we still do get them sometimes when we divide. So we'll talk about this shortly here. And then if we have expressions where you have right here, if we simplify this one, again, the same bases get to go together. So I can say that x to the 5th times y to the 7th over x squared times y cubed is going to be x to the 5 minus 2 times y to the 7 minus 3 equal to x cubed times y to the 4th. I feel like there was something I wanted to say about this. Oh, I know what it is. So, no, I'll say it later. We're not, yeah. We need one more thing before I can say the thing I want to say. So far we've got a couple rules. And now I want to kind of address something. Again, I know I'm saying, most of the stuff I'm saying is probably things many of you are aware of, but it's okay if you're not. right? Sometimes you might have learned this before and forgotten it. You might have never learned it before. It's okay. So what I want to talk about now is, well, first of all, what's 2 to the 0 equal to? You guys can show me on your fingers. You can, yep, you can tell me. I can only see like a couple of you right now. That's all right. 2 to the 0 is definitely equal to 1. The more important question is, why is it equal to 1? And that's what I want to talk about for just a minute. So there's, in my opinion, 2 equally good ways of explaining why this is equal to 1. There are probably other ways as well, but here's one of them. So here's one explanation. In fact, I will just say the explanation in general is because the additive law of exponents has to work the way we said it works. So because we know that a to the r times a to the s is equal to a to the r plus s, this law that we have all decided together is going to work the way it works is the reason why 2 to the 0 has to equal 1. So let's check it out. If I multiply 2 to the 3rd times 2 to the 0, if I use the additive law of exponents, I get 2 to the what? Well, I have to add those. So I get 2 to the 3 plus 0. The 3 plus 0 is just 3, so I get 2 to the 3rd. And 2 to the 3rd is equal to 8. It's my favorite number, by the way. I was born on 8/8. Won't be on the test, but it's good to know your teacher. I just had it. Well, you guys know. I told you my birthday was a couple weeks ago. Anyway, 2 to the 3rd is 8 times 2 to the 0 is equal to 8. 8 times a number is equal to 8. This number, the only option, this has to be equal to 1. There's no other choice, right? If you multiply 8 times something and get 8 back, you're done. It's got to be 1. So 2 to the 0 has to equal 1. And this reasoning works for any non-zero base, right? It's also true if I said 5. I know it's going to feel silly, but I'm going to repeat the same argument. I'm going to do it faster this time. So if I want to talk about 5 to the 0, well, 5 to the 0 times 5, to pick any power you want, I'm going to pick 5 squared. Pick any easy to evaluate power you want. That's equal to, well, add the powers, but 0 plus 2 doesn't change 2. It's still 5 to the 2nd. So I've got a number times 25, right? 5 squared is 25, equals 25. That's got to be 1. There's no other choice. A different but equally good way of explaining why it's true is by using the subtractive rule. If you said instead, actually let me use 6. What's 6 squared divided by 6 squared? Well, 36 divided by 36 is definitely equal to 1. But if I use the subtraction rule, that's equal to 6 to the 2 minus 2, which is 6 to the 0, which is 1. So there's another different way of explaining it if you like. I've even heard some students say something like this, right? Like 2 to the 3rd is equal to 8. And then to get 2 squared, you divide by 2. And then to get 2 to the 1st, you divide by 2. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. And that is also an equally good way of seeing it. In fact, powers of 2, as you increase the power of 2, you just keep multiplying by 2. As you decrease the power of 2 by an integer, you just keep dividing by 2. So we'll see in a second here that 2 to the negative 1 is 1/2. And 2 to the negative 2 is 1/2 of that, which is 1/4, and so on. So I should make a blanket statement though. So generally, a to the 0 is equal to 1 for a not equal to 0. It is important here that a is not 0 because 0 to the 0 is actually not defined. So 0 to the 0 is actually called indeterminate. Indeterminate. And indeterminate is a little more well, it's actually kind of less specific. It's less specific than undefined in that it means it, depending on what kind of expression you have, it can actually kind of take on any value. So 0 to the 0 is something that can kind of end up being anything, and we don't know what specifically it ever is. So it's indeterminate, more generally undefined. Two things I want to say about this. -3 parentheses to the 0th power is equal to 1. For the same reasons all the other things, right? -3 to the 0th times -3 to the 3rd equals -3 to the 0 plus 3, which is 3. And -3 to the 0th. -3 cubed is -27. -3 cubed is -27. This has to equal 1. But I want to point out, -3 parentheses to the 0th power is equal to 1. -3 to the 0th power is not equal to 1. It's equal to -1. Because here, if we read this, right, if we think about the order of operations, no one has specified what comes first. So we always have to think about, well, if it's PEMDAS, you have parentheses and then exponents come next. So this exponent, the 0th power, has to get done before this subtraction here. So it's really, when you read this, you should read it as -3 to the 0th, which is -1. So be careful. If you've got it like this, it's definitely equal to +1. If you've got it where the negative's on the outside, you do the power first, and then you get -1. For the same sort of reason, I'll just point out, right, it's the same reason that -3 quantity squared is equal to +9, because you get -3 times -3, whereas -3 squared is really equal to -3 squared, which is -3 times 3, which is -9. So an important distinction. Okay. Again, please don't hesitate to chime in if you have a question or a comment or an observation. Let's see. Yeah, cool. All right. So now, I know I mentioned before, we have negative exponents. So what is 2 to the -3rd? Well, no, not these ways. So I'm going to use my additive law of exponents to show you what it is. You probably know, you might know it's 1 over 2 to the 3rd or 1 over 8. But here's why. So 2 to the -3rd times 2 to the +3rd. Well, if I add those exponents, I get 2 to the -3rd plus 3, which is 2 to the 0, which we know is equal to 1. So here's what I have. I have 2 to the -3rd times 2 to the 3rd is equal to 1. But I want just this by itself. So I'm going to divide both sides by 2 to the 3rd. Dividing by 2 to the 3rd, the 2 to the 3rd and the 2 to the 3rd divide out. Right, 2 to the 3rd divided by 2 to the 3rd is just 1. So I'm left with 2 to the -3rd equals 1 over 2 to the +3rd, which we can write as 1/8. But this is the part I care about. So if you ever have a negative power and there's a good reason to make it positive, the way you make it positive is by putting it in the I like to put it in the place where it isn't. Meaning, if you have a 2 to a negative power in the numerator, then you bring it down to the denominator and make it a positive power. If you have 2 to a negative power in the denominator, you bring it up to the numerator and you make it a positive power. So whenever you change the place it is in the fraction, whether in the numerator or the denominator, you're always changing the sign of the power. I think it's water. There was something in my brain that I also needed. Oh, I know. Yeah, okay. I got it. So, a few examples. Actually, a general and then an example. Generally, we have that a to the negative r is equal to 1 over a to the positive r. And I mean, some examples of this, 5 to the negative second was 1 over 5 to the positive second, which you could write as 1 over 25. Negative 3 to the negative fourth is equal to 1 over negative 3 to the positive fourth. 3 to the fourth, so I definitely wrote out in the homework assignment whether I want you to kind of find a final answer or leave it as a power. Some numbers definitely, like 3 to the fourth is kind of on the edge of how big of a thing you kind of are expected to be able to multiply out and still know. I think 3 to the fourth is reasonable. So here's how I always do 3 to the fourth. 3 times 3 is 9, times another 3 is 27, times another 3 is, that's not how I do it actually. I do 3 times 3 is 9, 3 times 3 is 9, 9 times 9 is 81. That's an easy way to know that 3 to the fourth is 81. And negative 3 to the fourth is also 81 because you have 4 negatives multiplied together gives you a positive, right? Negative 3 times negative 3 is positive 9. Negative 3 times negative 3 is positive 9. And 9 times 9 is 81. And, you know, x to the negative 6 is 1 over x to the 6th. And then finally, 1 over 2 to the negative 5th, you could write that as 2 to the positive. Actually, I skipped a step. 2 to the negative 5th, I could write as 1 over, so 2 to the negative 5th, I could write as 1 over 2 to the 5th. And then when you divide by a fraction, you flip and multiply. So this is really 1 times the flip or reciprocal of this, which is 2 to the 5th over 1. But 1 times anything is itself. So, right, I mean, the 1 times and the divided by 1 don't really matter. This is just 2 to the 5th. So what I also want to say about this rule is that not only is a to a negative power equal to 1 over a to the positive power, but a to a positive power is equal to 1 over a to the corresponding negative power. And then more generally, if you move where you are, if you move from the numerator to the denominator or from the denominator to the numerator, you're just changing the sign of the power. Or a negative power gives you a reciprocal. There's one more thing I wanted to say about this specifically, and that is that this kind of lets us see that the subtractive rule is really just the additive rule with negatives. Oh, and I see someone clapping for me. Thank you for the clapping. I appreciate. I'm assuming you're clapping for me and not someone else. You can clap for everyone. I like the clapping hands. Thank you. I'll take any kind of applause I can get. So what I want to point out is that before we said a to the r divided by a to the s is equal to a to the r minus s, but really it's because of the additive law of exponents. So if you look at, say, let me make sure I wrote that the right way, actually. One sec. Yeah. So instead of saying that, instead of just jumping to the end conclusion that we can subtract these, here's what I'm really actually thinking of. A to the r divided by a to the s is really just a to the r times 1 over a to the s. But then 1 over a to the s is just a to the negative s, right? I bring it up to the top. I change the sign of the power. And then when I multiply these two things together with the same base, I'm going to add the powers. So I get a to the r plus negative s. So I should just write that as r minus s as the power. So this division is really just multiplication hiding. And that's actually always true. If someone says you're dividing, you're really just multiplying. Like if someone says divide by 3, they might as well have said multiply by 1/3, right? Division and multiplication are really the same operation. They just work slightly differently. They're just each other in reverse. The same is also true for addition and subtraction. They're really the same thing, just with negative numbers instead of positive numbers. I know it's weird for someone to say, I remember when someone said that to me at first, I was like, wait, multiplication and division are the same thing? Yeah, they're the same thing. They're just defined a little differently, but they still use the same principles. Okay. There was something else to say there. All right. Okay. So then, 15 minutes, all right, I'm good. What about fractional exponents? Like, for example, 9 to the 1/2. What does that mean? Or I'll ask a different question. Does anybody know what 9 to the 1/2 is supposed to be equal to?
Square root of 9.
Exactly, the square root of 9, which is 3. And I'll remind you guys, it is just 3. It's not plus or minus 3 because, right, we're not solving the equation x squared equal to 9. So whenever you're taking a square root, just remember you get a positive answer out. Whenever you take an even root, you get a positive answer out. Whenever you take an odd root, it actually depends. So we'll talk about odd roots just a second. But the question I want to answer first is, sure, 9 to the 1/2 means the square root, but why? Well, the answer, just like every other answer today, is because of the additive law of exponents. Every question I ask, the answer is the additive law of exponents. So here's why. Because 9 to the 1/2 times 9 to the 1/2, if I add those exponents together, 1/2 plus 1/2 is just 1. So here's what I've got. Well, first of all, I should say, right, 9 to the 1 is just 9. Maybe I failed to say that, and I will point out, right, for any base, a to the 1 is just a. That's always true. Just like a to the 0 is equal to 1, a to the 1 is equal to a. Because it's the number times itself one time, which I know sounds kind of weird, but that's the language we use. So now you're looking for a number, 9 to the 1/2 times itself is equal to 9. Well, the only positive number that you multiply by itself to get 9 is 3. So when you say the square root of 9, you're really saying the number that if you multiply it by itself, you get 9. 3 times itself, another 3 is equal to 9. So I just want to point out a language kind of issue here for myself personally, and maybe for you. 3 to the 1st is equal to 3. And the weird thing we say, which is something we just say, is that 3 to the 1st means 3 multiplied by itself just once. What I should really be saying is it's just there is one instance of 3. And you're not really multiplying it by anything. It's just kind of 3. Whereas 3 squared means 3 times itself again, or 2 instances of 3. But when you have just a 3 times another 3, right, we often say it is 3 times itself. So I don't want to be confusing about this, right? 3 squared means 3 times another 3. 3 to the first means, I don't want to say 3 times just itself because that sounds wrong. It's just one instance of 3. That's it. That's all I'm going to say. Okay. Hopefully that's not too confusing. I feel like the words here are not good with the math sometimes. So here, when you're looking for a number multiplied by that number again, equal to 9, the number has to be 3. So that's why a 1/2 power is a square root. So, for the same sort of reason, 25 to the 1/2 power is equal to the square root of 25, which is equal to 5. You don't even have to write this part here. We could just say it's equal to 5. Come on board. Because 25 to the 1/2 times 25 to the 1/2 is equal to 25 to the 1, or 5 times 5 equals 25. So when I think of a 1/2 power, I'm not finding 1/2 of the number. Right? Half of 25 isn't 5. Half of 25 is 12.5. I'm kind of thinking of half multiplicatively, meaning I'm cutting this in half by division. 25 divided by 5 gives you 5 back. You've kind of cut it into 5 with 2 factors. So you've got a half of it here and a half of it here and a half of it there. Right? 25 is 5 times 5. Each factor is equal. So you've cut it into 2 equal factors. That's a decent way of saying it. Maybe. Okay. 8 to the 1/3. So now you're looking for a number. Well, we're actually looking for a number that is equal to, So here's the way I kind of think of it. Before I wanted to multiply enough of them together so that my power was 1. I want to do the same thing here. 8 to the 1/3 times 8 to the 1/3 times 8 to the 1/3. 1/3 plus 1/3 plus 1/3 is 3/3. 3/3 is equal to 1. 8 to the 1 is just 8. So I'm looking for a number that when I multiply it by itself 1, 2, 3 times, I get 8. And what's the number have to be?
2.
Exactly. 2 times 2 times 2 is 8. So I'm thinking about 8 broken up into 3 equal factors that multiply to 8. And yes, 8 to the 1/3 is the same as the 3rd root of 8, which is 2. So, okay. I might ask for a few extra minutes today. Sorry. Couple more things. So first of all, we have that generally a to the 1 over n is the same as the nth root of a. And some examples of this are, for example, 81 to the 1/4 power, or the 4th root of 81. That's going to equal 3. Because 3 times 3 times 3 times 3, which is 3 to the 4th, is equal to 81. All right, so if I'm looking for the 4th root of 81, or 81 to the 1/4 power, I'm looking for a number multiplied by itself 4 times to equal back to 81. Or, for example, 32 to the 1/5 is the 5th root of 32, which is equal to 2. Because 2 times 2, because 2 to the 5th is 32. Let's just say it that way. And I will also point out negative 32 to the 1/5 power, or alternatively, the 5th root of negative 32 is equal to negative 2, because negative 2 raised to the 5th power is negative 32. It is always possible to take odd roots of negative numbers. You can take a cube root of negative 8, or the negative 8 to the 1/3 is also negative 2. Because negative 2 times negative 2 times negative 2 is equal to negative 8. You cannot take even roots of negative numbers. At least you can't and get a real result. Right? The square root of negative 9 is imaginary. Sorry, that looks terrible. And we're, at least currently, we are not worrying or concerning ourselves with imaginary or complex numbers. So we're just going to leave that alone. 4th root, 6th root, 8th root, you can't take any even root of a negative number and get a real number. And the reason why is because there's no real numbers that if you multiply them together, I say if you multiply a number by itself, it comes out to be negative, for example, right? If I wanted, negative 9 to the 1/2 power times negative 9 to the 1/2 power equal to negative 9 to the 1, I'm looking for a number times itself again equal to negative 9. But a number times a number, if the number is positive, then the result's positive. If the number is negative, then the negative times the negative is still positive. So this doesn't work. How much have I got left here? Okay. Yeah, I think I'm all right. Okay, the last, maybe not the last, but almost the last rule is, again, still because of the additive law of exponents. An example is 2 to the 3rd to the 4th. So here we're not multiplying two bases together with different powers. We're taking a base to a power to another power. And it still has the same type of meaning as before. If you've got something to the 4th power, it means you've got that something times itself 4 times. So I've got 2 to the 3rd times 2 to the 3rd times 2 to the 3rd times 2 to the 3rd. And at this point, I could use the additive law of exponents to say, oh, when you multiply things that have the same base together, we just add up the powers. So that's going to be 2 to the 3 plus 3 plus 3 plus 3, which is really 2 to the 3 times 4, which is 2 to the 12th. So when you have a power to a power, we multiply the powers. So generally we have that a to the r to the power of s is equal to a to the r times s. Or as I say, when you have a power to a power, you multiply the powers. Okay. A few examples here. 3 to the 5th to the 6th is equal to 3 to the 5 times 6, which is 3 to the 30th, which is really big. And then I should say this rule before I talk about it. Oh, that got kind of weird, sorry. We also have a rule, which I thought I wrote down somewhere, but oh yeah, I do, yeah. So before I do more examples, we also have the following rule. We have that if you have things multiplied together or divided together, all raised to a power, you basically just distribute the power across the multiplication of the addition. So a times b to the r is equal to a to the r times b to the r. And a over b to the r is equal to a to the r over b to the r. We've definitely used, especially this part of the rule, like when we've been squaring trig results, like the square root of 3 over 2 squared. We definitely just said is the square root of 3 squared over 2 squared, which is 3 over 4. And we've definitely used that rule before. Okay, I'm gonna ask for 5 extra minutes. Usually I wouldn't, but I'm gonna have I'm giving you guys a homework assignment that's due tomorrow on this. So I do want to get through a few more examples just to make sure you've seen the things you need to see to be able to do the homework. So we'll end class at 2:25, I promise. My alarm's gonna go off, that's all right. So a couple more examples of this. For example, if you have like 2 times x cubed times y to the 4th to the 5th, you would just give that 5th power to each of these things. So you have 2 to the 5th times x cubed to the 5th times y to the 4th to the 5th. 2 to the 5th you could leave as is or simplify as 32. X to the 3rd to the 5th, you would multiply the powers. You get x to the 3 times 5. And y to the 4th to the 5th would be y to the 4 times 5. And then you would write that as 32, x to the 15th, y to the 20th. Another example, if you had, say, let's do this one, 9x to the 6th over y to the 8th quantity squared, you can just square each part. So again, I'm thinking of the power of 2 distributing to each of the independent factors. So we get 9 squared times x to the 6th squared over y to the 8th squared, which is going to be 9 squared is 81, x to the 6th squared is x to the 12th, and y to the 8th squared is y to the 16th. And then depending on how you want to write the answer, you could leave it like this. Sometimes they want all positive powers. Sometimes they want everything in the numerator. You could also write it as 81 x to the 12th, y to the negative 16. Yeah, you're good there. So there's a few examples on these last couple pages that I'm not saying, but that's all right. The last thing I want to point out not getting scared of my alarm. Congratulations. The last thing I want to point out are interesting fractional powers. So yeah, we'll do that. Sorry, come on, thumbs. So more complicated fractional powers. Like 8 to the 2/3 power. So there are numerous ways of dealing with this, and there's probably one best way. So first of all, the long way you can think about this is, well, 8 to the 2/3 times 8 to the 2/3 times 8 to the 2/3. 2/3 plus 2/3 plus 2/3 is 2. Right? 2/3 plus 2/3 is 4/3. Plus another 2/3 is 6/3, which is 2. So I have a number times a number times the same number times the same number equal to 64. And what number do I multiply by itself 3 times to get 64? 4. So 8 to the 2/3 power is equal to 4. But this isn't the way I would actually find it. The way I would find it is the following. So whenever I have a fractional power like this, where the numerator is not 1, right? Like, because like if it was 8 to the 1/3, you would just take the cube root of 8 and get 2. But if it's 8 to the 2/3, I really recommend you write 8 to the 2/3 power as a power to a power. So 8 to the 2/3 is equal to 8 to the 1/3 to the 2nd. Right? 1/3 times 2 is equal to 2/3. So that these expressions are the same. 8 to the 1/3 we know is the cube root of 8, which is equal to 2. And 2 squared is equal to 4. You can do it the other direction, meaning you could alternatively break it up as 8 squared to the 1/3 power. Right? These powers also multiply to 2/3. This way I find more challenging. 8 squared is 64. 64 to the 1/3 power is the cube root of 64, which I do happen to know is 4, but feels harder to know than the cube root of 8. Let me give you guys, I've given myself 2 more extra minutes. Let me give you 1 or 2 more examples, and they'll be quick. Thank you for the extra time. I do appreciate it. I will try to give it back to you someday, but I probably won't. Maybe I'll give it back. I would say I'd give it to you on an exam, like I'd give you extra time on an exam in like a real classroom setting, but since that is not what we're doing, that's not a really good promise. So I'll do something, probably, maybe. Okay, 9 to the 3/2. Here's the way we want to do this. We want to write it as 9 to the 1/2 to the 3rd. Because 9 to the 1/2 is just the square root of 9, which is not hard to calculate. And 3 to the 3rd is 3 times 3 times 3, which is 27. So 9 to the 3/2 power is equal to 27. And then I also want to point out, because it's pertinent, that 9 to the negative 3/2 is going to be almost the same. What does the negative power do for us? It flips or reciprocals. So 9 to the negative 3/2 is going to be 1 over 9 to the positive 3/2. And then we already know that 9 to the 3/2 is 27. Okay, here's my last quick example in 1 minute or less. 27 to the negative 4/3. I kind of ignore the negative power. I'm gonna look, I really like, if I was gonna do this, here's what I would probably do. I'd be like, okay, well, 27 to the 4/3 is equal to 27 to the 1/3 to the 4th. The cube root of 27 is 3. 3 to the 4th is equal to 81. So if 27 to the positive 4/3 is equal to 81, 27 to the negative 4/3 is 1 over 27 to the 4/3, which is 1 over 81. All right, here's the last word I want to leave you with. When you have a positive number to an exponent, the answer is always positive. Meaning, and here's why I'm saying this, 27 to the negative 4/3 is not equal to negative 81, right? It's equal to positive 1 over 81. So be careful, because this is a mistake that happens a lot. If you're doing these